Hi, today I'm giving the presentation of the flow process of formation of M1 in the wafer fab. So, so for the first one, for the formation of the M1 is using the photolithography, which is using the we will put a layer of photoresist, which is using the spin coat method on the panelized IDL. So the mask will be fully cover the wafer. So after that we will expose with the source, the light, and we will get the under the mask. So then we will develop and remove the develop and show the pattern of the show the whole of the photoresist. So after that we will creating the contact hole by using the etching. So in this we will remove the the pattern using a dry etch, which is plasma etch. So with this one, the etch will highly selective, stop at the specific uh, the layer, so we will reach the surface of the source and the drain by creating a narrow deep contact hole to the as shown in the diagram. So after that, we will remove the photoresist. So the photoresist is removed, and then we will clear the wafer surface as the next step is barrier metal deposition to ensure the reliability low resistance only contact to prevent unwanted reaction or diffusion between the contact metal under the relying silicon uh, barrier barrier layer such as titanium nitride is deposited using PVD or CVD. The use of titanium nitride because it can provide a barrier material between the silicon and aluminum, particularly for the extreme shallow connection that make a good contact but doesn't react with the aluminum, as this is a critical as a common interaction metal like aluminum tends to mix with the silicon at a high temperature. So for the next is contact metal filling. The contact metal filling, we using the aluminum to fill the empty space after the barrier material is added. So the aluminum we will fully cover the wafer as well. So as the aluminum is used as a low cost and excellent electric conductivity and the good thermal conductivity. So for the next, we're using the CMP method, is a chemical mechanical panelization to remove the unwanted layer for the wafer. So the excess metal from the top surface of the IDL will be removed via this. So by leaving a metal within the contact hole, and now the flush with the LDL surface. So this normally we can call as the M0 or M1 as a VR1 as a local interconnection. So for the lastly, we will deposit the metal one as interconnect line deposition over the entire surface, the covering filled with the IDL. So for the material use, we normally use a copper or aluminum used for the as a M1. So after that, the lithography will continue by doing the next step, by creating the M2 until the M15. They will continue by using the different type of material such as boron or something other that to make it to form a circuit. So there are three critical reliability problem to solve the single reliable M1 connection to make the proper electric contact or detecting the source and drain. The first one is the ohmic contact formation. Ohmic contact formation involve creating a low resistance, non-rectifying radical junction between a metal and a semiconductor by reducing Shapley Berry. This is achieved through a method like using the high doping of semiconductor surface, which surface preparation and curing, and post-metallization annealing, which promote the diffusion and the formation of compound like silicate and other techniques including using a specific metal semiconductor combination such as a surface treatment or inserting the interface layer to improve the carrier transport and reduce the specific contact resistance. So in the early history of the wafer, the integrated circuit visual primary use material for use for contacts are aluminiums. So when aluminium contact with the p-types and p-type, typically the yield is good in ohmic contact. However, there are some issue develops when attempting to connect to the n-type, which is under same picture in the diagram picture. So aluminum can produce a metal semiconductor Schottky barrier diode slightly doped in n-type material. So to prevent the rectifier contact from mating, an N diffusion is put between aluminum dot slightly dot area to show in the figure. We can get the graph like C. So we resulting the particle ohmic contact with the when IV characteristics similar. So however, the copper has become largely replaced by aluminum as the main contact layer due to its low electrical resistance, so and better resistance to electromagnetic migration. And there are such and other materials such as tungsten also used as the fill the small and deep vertical connection and the first layer and for the metal wiring. So it has superior gap filler property in this structure. The next of the problem is the aluminum spiking and junction penetration. As a diagram below, we can show the silicon aluminum axial point occur at the temperature of 577 Celsius at the contact allowing temperature between 450 and 500 Celsius. The aluminum will absorb 0.5 of from the 1% of the silicon. So after upper deposition, aluminum is usually annealed at 450 until 500 Celsius to provide a good contact formation. But the silicon will penetrate into the aluminum even at this temperature, which is far below the active limit. This will result junction spiking. So aluminum spiking or junction spiking is a process of failure mechanism in a semiconductor device where the aluminum used to metallize the penetrate to the silicon junction, potentially will causing the short circuit of the design. So the short circuit design will cause the circuit fail. So this occur due to the catalytic reaction and the diffusion between the aluminum and the silicon is relevant to the temperature, especially during the excessive contact process. So the standard method to solve the aluminum spiking and junction penetration is using an aluminum alloy, or is already saturated with the silicon, which is about the 1% silicon and 99% of the aluminums. So this spiking will avoid this aluminum silicon alloy does not require the silicon from the wafer. However, there are some other methods such as provide the barrier material such as the silicon and aluminums, particularly for the extreme shallow connection. The barrier metal such as make a good contact but does not react with the aluminum such as the titanium or tungsten. Lastly, I will discuss about the electron migration. Electron migration is the movement of the metal atom within a conductor caused by a transfer of momentum from flowing electron. So this phenomenal reliability issue in a microelectronic device can cause a graduate displacement of atom leading to the formation for void that can break the connection, will cause the open circuit for the design. For polyhole metal accumulation that can cause a shock. So for the high density, high temperature and certain material property to increase the rate of electron migration, such as the picture in the above. So, uh, scanning using a electron micrograph or aluminum interconnection. Uh, will- this is a failure caused by the electron migration. Sparse with the aluminum with 0.5 copper, and the second picture is evaporate aluminum with 0.5 copper. So there will explanation using the Black equation. The Black equation is an empirical model, a model used to estimate the median time to the failure for the NTF or NTDF for the semiconductor interconnection due to the electron migration. So this is a formula for the NTF is J exponent into EA over KT. So for what is the J is current density in the interconnection, then the N is a factor scaling factor range between 1 to 2 depending on the diffusion process. So the case the Bowman constant and the T is temperature, and the EA is the activation energy. So for the above equation is defined as a proportional with the proportionality constant determined by as a function in the area. So in general, large connection will have a longer MTTF, since the EA can also be expressed in the EV. So K must be let it be translated to the EV using electron charge. The aluminum is a alloy with a tiny amount of heavier metal such as copper to use to increase the reliability. So as a result, a spectral deposition method frequency employed a target made by the alloy like 95% of aluminum, 4% of copper, and 1% of silicon. This offered electron micro resistance to stop aluminum from spiking. Uh, Other than that, the switch to the pure copper for internet improved the electron micro resistance also as well. So this is all from me. Thank you very much.